Good morning from our Boston Regional Training Center here in Nashua, New Hampshire. I'm Matt Schwegler, along with Ron Lucier for today's tutorial on the basics of optical gas imaging. Morning, Ron.
Hey, Matt, how are you?
I'm doing really well. How about you?
Fantastic.
Good, good. We'll get started in the session here in 1 second. I want to first do a couple quick housekeeping items. For those of you who might be interested in getting certified, infraredtraining.com is where you can go to see ITC's latest training schedule. That's for classes in the US and Canada. And for our fellow thermographers based in Europe, the Middle East or Africa, irtraining.eu is where you'll find a list of courses in your region. All right, with that, I'll toss it to Ron, and we'll start today's presentation here on the basics of optical gas imaging. Ron.
Yeah, thank you. Well, today we're just going to do an overview of optical gas imaging, what it is, what it has been, and we're going to look a little bit to the future, some of the newer things that we've added to the capabilities. So we just want to talk about some of the capabilities of the gas cameras, review some applications, and our future developments are, I think they're kind of really exciting, particularly the software end. So what is OGI? OGI stands for Optical Gas Imaging, and that's where we use either handheld or fixed mount cameras, which are dedicated to the sole purpose of detecting leaks of certain gases. Yes, they can do much more than that. They can measure temperature. One common question we always get is, can I use my OGI camera to do a regular inspection? Absolutely, but these are always filtered for a specific gas. And the main advantages of OGI cameras are their portability, usability, sensitivity, and the broad range of gases that can be detected. Now, these are primarily hydrocarbons, but there are others such as carbon dioxide and sulfur hexafluoride. We make a variety of cameras. Very important, we're starting pretty much all of our presentations now talking about safety. The first purpose of your IR camera is your personal safety. We want you to go home to your families at night and do so nice and healthy and safe. So make sure the area you're inspecting is very safe. And one of the easy ways to do this is to make sure that you are wearing all the required personal protective equipment. So whatever is specified for you, including any gas monitors, hard hats, safety shoes, safety training, make sure that is in place before you go out to a job. And it's very easy to become complacent. One of the things that I strongly recommend is a situation like this where if we're going to approach an area, this is a large gas compression facility, just stand back from a long distance, go ahead, take a look at the equipment both in auto and in the high sensitivity mode of the camera. And if you don't see any large leaks, cut that distance in half and repeat that process. And maybe depending on what the facility is, you might want to do it again. And what you do by doing that is you assure yourself that there are no gargantuan leaks, that there are no large leaks, and there are no middle-sized leaks. And so all that's left are the small leaks to go chase up close and personal. And again, there are a lot of facilities will have either a berm around components or they'll have some sort of standoff distance that you're required to stay behind. And with lenses, et cetera, you should be very easy to see most of those. However, all equipment in buildings also should be inspected for any significant leaks. The following video is inside a compressor building. We walked in there, the inspectors were very focused on a pretty obvious small leak, and they missed initially a very larger leak in the background. And the readings were as high as 20% LEL. That's the lower explosion limit in that area. And so that was a very significant environment to be operating in. And so here we can see in the auto mode a number of folks walking around. They're looking in the auto mode of the camera. You might not be able to detect any leak that's in the background. And so that's where our high sensitivity mode comes in. And behind this compressor set here, there was a valve cap that was leaking, and methane being lighter than air, it floated up. And initially when these folks were looking at the leak on the left, they were not aware of the leak behind them. And with gas moving around inside a building, that could have been a hazardous situation. And that's what we look like visually. So the leak was back there. Also, the OGI cameras, they show us the invisible, things we wouldn't necessarily see. Oops, let me play this video here. This is from our original gas finder camera that we brought to market in 2005. And you see the vapors coming off the top of that tank. That hatch was open. That inspector is dropping a weight down to the bottom of the tank. This is a process called tank gauging. And if it looks dark, the person who took the video chose to show a black plume against a white background, so the color palette is inverted. And it really doesn't matter that much. It's up to the inspector to decide whether they wish to do this or not, but you can just see the type of environment that that person was operating in. It's quite hazardous. And that original camera, that particular date, did have a high sensitivity mode, but it wasn't as robust as the one that we have now. So we have a lot of different GF cameras. We have cameras that can see some refrigerants, sulfur hexafluoride, which is a gas that's used in circuit breakers, ammonia, and some hydrocarbons. The GF306 is particularly suited for looking at for ethylene. And for anybody who's cracking ethylene, this is an ideal camera to find leaks. Yes, you can see the ethylene leaks with the GF320, but you can find smaller leaks with the GF306. It's a little more sensitive. Then we have our 300 and 320 series, and those are our hydrocarbons, and those are available for both fixed mount and handheld. The 343, which is carbon dioxide camera, that can be used as a trace gas for leak detection, and a carbon monoxide camera, the 346, which is good for, particularly in the steel industry where they're using a lot of carbon monoxide. Now, as far as the regulations go, in June 2016, the US EPA published an amendment to the existing regulations, and it's known as Quad OA. And it recognized optical gas imaging as the best systems for emission reduction. And they did a whole series of studies. The white paper is listed later in this, I think the next slide as a matter of fact. And they found out that they could find more leaks quicker with OGI than they could with a sniffer. And while the sniffers have a distinct advantage of getting a some measurement of the concentration of the leak, the OGI can see a broad area, and you can see if there are multiple leaks, in particular on flanges and gaskets. Quad OA, well, I won't say unfortunately, but it applies to newly installed compressors, wells, and associated equipment. So it doesn't really fall into the category of refineries and ethylene plants and chemical plants and other facilities. But it's mostly for the oil and gas industry, the upstream stuff. And so here's EPA's statement on optical gas imaging. The EPA's analysis for the proposed rule found OGI to be more cost-effective at detecting fugitive emissions than the traditional protocol for that purpose, which is Method 21, a tried and true and very well trusted technology. And EPA therefore identified OGI as the best systems for emission reduction for monitoring fugitive emissions at well sites. And there's the reference to the federal regulation in the Federal Register. And so in their final subpart, they recommended oil and gas well sites be inspected twice a year, compressor stations quarterly, and the natural gas processing plants had no existing change from that regulation. Now these regulations are changing all the time. I know there have been some proposed amendments to Quad OA and the methane rule. I don't know the current status of that. I don't think anything has been published in a final form at this point, but that could happen at any time. Now, one of the key paragraphs from the Quad OA rule is that any component has a potential to emit fugitive emissions of methane or VOC. VOC is a volatile organic compounds at a well site or compressor station, includes but not limited to, which means you better go take a look at everything. And this is where OGI has a real advantage over the traditional Method 21. We can see the occasional crack in a well that might be leaking hydrocarbons that might not be picked up by another technology, but it can be visualized. Students in our classes reported success in doing that. And also you get a big overall view of the area. And if there aren't any leaks, you can document the fact that there are no leaks. And so if you have excellent repair procedures and components, finding the fact that there is no leak is probably as important as finding that there is one. So they imply that you look at everything. No tagging of the OGI for identified leaking components is required. So you don't have to put a physical tag on that. And I think their thoughts there were that if you were to go up and have to tag something, you might be violating some setback or some safety barrier. Method 21 is allowed, but it does require tagging. So you document the leak with the optical gas imaging, and I don't even believe in some cases that you have to store the video or store the image. But you have to submit plans. The documented plans are required, and it seems to be working fairly well from the folks who've been training. There are also some other general requirements. How frequently you do the inspection, and that varies from facility to facility. The technique that you're going to use, if you're going to use OGI and Method 21 to verify it, I think it's a wonderful way to do that. They want to know the manufacturer of the test equipment, procedures, time frames. It's a lot of documentation. But two important things that EPA calls out is the training and experience of the operator. And there are some folks that have just come into class that have been handed an OGI camera, and they say, well, next week I have to go inspect this equipment, and I've never really been to a compressor station. And so I think that's what they're really addressing. And so the additional training that folks are getting on site in their facilities, and the hands-on, the mentor training, I think has been working very well. And you also have to have a procedure for calibration and general maintenance. We'll talk about that in a moment, okay? So the training and qualification, very important. We wrote the first optical gas imaging training course that was commercially available back in 2005. And it still is one of our most popular courses that we teach. And we train regulators, we train industry, and it seems to be going very well. And so getting some good training is just no substitute for it. Also, the calibration and maintenance is a really good idea to send these cameras back annually for maintenance check. But if your task is only to image gas, you do not have to get a temperature calibration for the GF cameras. And that's been in our manual since we started producing these. And that's paragraph 3.2 in this manual that I think is the general GF series operators manual. So it says no recalibration recommendation. And so the ability to detect gases is not affected by how accurate your camera can measure temperature. It's always filtered, and it will always image gas if there's any present. Also, Quad OA said there should be a process for initial and daily verification checks. Fantastic. Just last week I had a class, and one of the students turned his camera on and looked at another student. That student was 145 degrees Fahrenheit. And whoever had the camera before was playing around with the parameters, emissivity. He says, hey, lesson learned. And I said, that's in all of our courses, so a verification check that the camera leaks is not a bad thing. And also, extremely important, is to ensure that we have adequate thermal background. And the gas cameras work on the principle that the gas is going to absorb energy from somewhere, and it's not going to make it to the camera. So the background is what you're looking at, and the gas would be between you. You have to make sure that you just have enough sensitivity there. And I've tested these cameras down to ridiculously low levels and have still been able to see very, very, very small gas leaks, but I'm not quite sure, it might be under ideal conditions. Also, you should note that there are some adverse monitoring conditions. If you're in an area that's subject to a lot of wind, a lot of dust, dust floating through the air is going to look very similar to a gas cloud. So it's a matter of, really goes back to training the person's subject matter expertise. And if you have a max wind speed procedure, we did on our FLIR.com/OGI, I'm not sure if that's the current URL for it, but we did have some max wind speed procedures. We were testing leaks, I think up to about 20, 25 miles per hour, somewhere around there. But they had to be fairly significant leaks. And the EPA said that this really is one of the best methods, if not the best method, for getting and identifying leaks at the difficult to monitor components. Those would be those that are in a pipe rack and nest of pipes up high, and difficult to access any other way. And you can and we have identified some significant leaks that way. One of the most difficult is how do we do that daily verification check, and how do we ensure adequate thermal background. We'll talk a little bit later on about quantification, and ensuring the thermal background is very much part of that. The EPA gave little guidance on how to perform the verification checks. In the greenhouse gas rule, they gave you an equation, and they basically say, you know, look at a gas that's 98% or more concentration, and if you can see it, the camera still works. So it's, we discussed several options in our course. This is one way, a simple airflow meter, and I did this, almost, you know, a little over 3.5 years ago. And that's just a propane bottle. I don't think there's $150 in parts. I'll give you the part number here in a moment. And that leak was extremely small, and it's coming out the top little circle there. On top of it, you can barely see that there's something there. In the auto, that doesn't always give us the best image, so we have the ability with our cameras to thermally tune. We adjust the temperature, span, and level, and there's our little leak. And that was less than 5 grams an hour, which is not a very large leak. And then going into the high sensitivity mode, the HSM is, mathematically, it's kind of like the first derivative of the video. And so it's the difference of frames, and we just continually show you the difference of frames, and it has different sensitivities. At a sensitivity of 0, that would be for looking at very, very large leaks. 7, it's for 1. And the little black bead there is how much gas is being flowed up through that little flow meter, and that was as low as I could crack that. So I was pretty impressed by the camera. Pretty adverse conditions. It was kind of windy and overcast, and it had just rained, I believe. So these are the part numbers. This will be in the presentation. If anybody needs a PowerPoint presentation on how to build a portable meter, you can just contact me, and I'll be glad to give you all the parts. We don't supply those, but you share the design and the math behind it. So how do we detect gas? Well, we can see here is where the yellow arrow is, that is a methane leak, a natural gas leak. That was taken with a long wave camera. We do have our GF77 camera out now. That is a very portable, more affordable, less expensive, more affordable camera. And it can detect some pretty significant, or pretty impressive leaks. And very nice camera. But to detect or see a gas, several conditions must be correct. There has to be energy for the gas to absorb. If we were to take a gas and a gas leak inside the basement of a building, and everything's all the same temperature there, we would have a very difficult time seeing it. We might see some change in the index of refraction of the air, but it would be very difficult. So we need just some energy there. And we need a filter that corresponds to the gas absorption wavelength. And common question is, why do we have so many different cameras? Well, there are many different absorptions, many different gases to look, and they're not all the same, but we also need, again, adequate thermal background and cloud motion. The cloud motion is usually the easiest part, because these gases are either lighter or denser than air, and so they'll either rise or sink. And so our cameras are structured in something very similar to this, where we have a filter that's inside our camera. It's kept at the same temperature as the detector, which is right around liquid nitrogen temperatures, 77 kelvins, minus 321 Fahrenheit, minus 196 Celsius, somewhere around there. And so the energy comes in and it strikes that detector, and we don't see the effect of any filter that's there. So having the detector and the filter at the same temperature is a real advantage. This would be for the cooled cameras. Okay? So really, one way to think about this is if we have a radio in our vehicle and we want to listen to music, our radio can listen from 88 megahertz to 108 megahertz. And you wouldn't want to listen to all of the stations all at once. That'd be noise, nonsensical, etc. So you use a little tuner to find the type of music that you want to listen to, or talk radio. And well, that's basically what we're doing here. We have a detector that can see a broad band of wavelengths, but we're only interested in where the gas is absorbed. And so that's in simple terms, the process of filtering. Now, these are data taken from the NIST, National Institute of Science and Technology, and this is the yellow part here is the general shape of our filter. And the dark line here is how that gas, which here is propane, how it absorbs energy. And so really what we're doing is we're imaging the energy that is absorbed by the gas that corresponds to the filter that is above that line, and that's how much energy there is for us to absorb or image. When we go to another gas like methane is CH4, because of the quantum resonance, the different size of the molecules and their quantum bonds, it is a very somewhat symmetrical molecule, but it leaves us very little energy, but to image. But the cameras are so sensitive that we can still see extremely small quantities of methane. And so, even given the issues with very little area here for us, we're very successful at detecting natural gas leaks. And here's another one. CH4 is methane, C2H4 is ethylene, and that has an absorption in the mid-wave and also a big absorption in the long wave. And so you have a choice of either the mid-wave or the long-wave camera to look at, to image with. And so we can see in the long wave, I've always recommended an ethylene plant should get a long wave camera. You'll find smaller leaks than you would with a mid-wave, but it's a matter of choice. And if you want more gases, there's a resource there. There's a NIST chemistry web book. Lots and lots and lots of gases, lots of technical information. Most of that stuff I don't understand. So a few applications here. One question came up in class: can we see tank levels? If the tank is uninsulated, yes, you probably can under the right conditions. With what accuracy? That's yet to be determined. We haven't really done much there, but you can see tank levels. This particular tank had very little oil in the bottom. You see the bottom right there, but it had a pressure relief valve, an Inardo valve, which is both a vacuum breaker and a pressure relief valve that was leaking. And obviously a very windy day, this was a substantial leak. And this was found as part of our training class. They got it repaired before, I think it was repaired by the end of the day, if I remember right. And so it was the first time the yard had been inspected. Inside a compressor building, EPA recognizes that there are certain things that have to leak. And this is a level controller. This is on a separator. It can take out sand and water and other things that happen to be there. And if that valve was not able to exhaust the atmosphere, it could not work. And so that is a level controller. So these are exempt from the regulations. And the question is does that smell? No. This is right where they are taking the gas out and compressing it down the line. It hasn't yet had the mercaptan there. But it really shows how big those leaks can be indoors. Okay, and this is some well heads, and those well heads are leaking. As a matter of fact, I believe the casing was leaking, and we can see the gas coming up around the well heads, and as it pans to the right, we'll see it was actually coming up through the ground. And I don't think that this was a good thing to find. I think that this would require a fair amount of repair. I'm not an expert in that, but we can see to the right that the gas is coming up right in that whole well area there. And so sometimes we find some pretty significant findings. I believe this one was fairly significant. Okay, and there in the high sensitivity mode, we can see the leak. And going on to sulfur hexafluoride, which is a gas that's used in circuit breakers, that's a leak I believe was about 5 to 10 pounds per year. And so it's not a very large leak. We had one customer report to us a leak of about ½ a pound a year, which is not much gas. But these are 345,000 volt circuit breakers, and very easy to see exactly where that leak was. So when they go to repair this, they know what they're into, and they can figure out what the parts are. This should go to the visible here, so you can get an idea of what we're looking at. There it is. So these are large three-phase circuit breakers and switch yards, and very common, very helpful. Sulfur hexafluoride is one of the EPA gases in the greenhouse gas rule that have to be monitored and reported. And with a carbon dioxide camera, here's some cows. And this is in the high sensitivity mode, and like you and I, we inhale and exhale. Yeah, we could have done that in methane, and we have in our course material, we have cows that are burping, and but that, I think, was a pretty nice video to have. So looking forward, that's where we are. You can see the Method 21 over here and an example of an optical gas imager over there. What's coming down the pipe? Well, we already have the Class 1 Division 1 camera that's built on the GF320 platform. That's a GFX 320. And that drop video still horrifies me to see the cameras dropped. I would never do that in class and test it, but boy, I tell you, those cameras are rugged. And so these are certified for use in hazardous environments right here. And those cameras have gone through some pretty rigorous testing. And I think they've held up pretty well. I mentioned earlier the GF77, that's the one on the left, very lightweight, very portable camera, easy to use, comes with a couple of different lenses. And they've taken recently and released the GF77A, which is basically the imaging part of that without the display. And that would be for fixed mounting. You want to look at a compressor station, you want to look at a compressor and get an alarm if there's a leak. And so these are more affordable options. They're not quite as sensitive as the cooled cameras because of the different technology, but they work very well. And those cameras are sensitive to methane, sulfur dioxide, and nitrous oxide. Okay, there we go. Now, we've partnered with Providence Photonics, and we can now offer a quantification solution. Everybody from day one we were starting to do these presentations and training. Well, how big is that leak? And we didn't really have an answer. We could say, oh, it's little, it's big, it's massive. But the QL320 is a really novel solution. It's a tablet. If you want to use it live, you can do it on the field, or we have a recording mode that will help. And the important thing here, I mentioned the green area here, that indicates that we have adequate thermal background for detection. So this determines if your scene is set up properly, if you've entered all your parameters properly, and it can detect and quantify a number of gases. It's fairly simple to use. You can hook it up to the right. As you see, it's on a tripod. Or we have this Q mode that has been added to our latest batch of cameras, the GF620 camera and the GFX cameras, and then I think the Q mode can even be added to some of the older GF320 cameras. And what the Q mode is, it stores a whole sequence of images and all of the data that are required for calculating a gas leak. And so basically you have some background gas plume, you look at a source, and you record is anywhere between, I think, 300 and 500 frames, and then you provide an analysis. And so it'll give you a quantification in multiple units here. And also, we've been released, about a year or so ago, Thermal Studio software. And it is awesome. And so while most folks aren't going to do a lot of temperature analysis in the optical gas imaging world, this has a great feature, mapping. And so if you have the GPS signal on, GPS enabled on your camera, and you have a GPS signal, so this doesn't work inside buildings, it won't work in basements, etc. Every time you store an image, it's going to store the GPS signal, and you can batch process those your images in there, and it will make a map of where you were. Now this is, and for the folks that are out in the field, you get to a very large compressor station or processing facility, and you forget your notes. You can go back and look at a map and say, yep, that's exactly where I was standing. And I think this is one of the handiest features for the optical gas imaging world. You can also record a sequence in there and add high sensitivity mode to it later on and change a color palette and etc. So it's really awesome software. So that's kind of where we are and where we're headed. We're still going to be very busy. We're around all the time doing classes all over the country. Except here in New England, we really don't have much.
Not a lot of oil and gas.
Not a lot of oil and gas up to here, but we have done some courses here.
Yeah.
Mostly for the local regulators, and it's a lot of fun. So if you have any questions, you can contact us here, or you can contact me. We'll have our contact information. So that's where we are. I say thanks a lot, Matt.
No, thank you very much, Ron. So, I had a couple questions that did come in, Ron.
Sure.
Let's see, the first one from a little bit earlier, and I apologize if I mispronounced the name here, but it's Marilio. If I was using a DJI M600 drone package with a FLIR 300A OGI camera. Have you had any experience with this setup? Any challenges or limitations with that?
I don't fly the drones.
Okay.
And so I have no experience with that. But I do know that a lot of folks are flying the 300A, and they've been very successful
So
with
speak
it.
to that camera then, perhaps.
Yeah, the 300A is a fixed camera. It's a cooled camera, so it's going to be very sensitive on a drone platform. You should be able to get some pretty awesome images. You will be able to probably stay up above any leaks and fly, like pipelines. And we've had some videos that have come in from folks flying pipelines. They were done with helicopters. There's no reason why you couldn't do it there. I don't see any really challenges. I would say that daytime, not raining, and because you're going to get an adequate thermal background, and I think it'd be relatively straightforward application.
Excellent.
Good question. Yeah.
Great. Well, Robert was asking, what can be considered the test constant, and I want to get a little bit more information there. What can be considered the test constant in the initial and daily verification is checked against? I think what Robert was referring to is, sort of, you mentioned cloud cover and wind and things like that.
The daily verification check, what EPA says is you want to have a gas that is at least 98% pure. They did most of their testing. We did most of the testing for EPA with a 50-50 mixture of 1% dilute methane and propane. It was 10,000 parts per million. But they don't require you to do that. So you can pick any gas you want, but it has to be a gas that's within the waveband of the camera. So I don't think that if you had a GF306, if you use propane, that would be appropriate. You'd have to use ammonia would be cheaper than putting sulfur hexafluoride in the atmosphere. Okay. So it's a 98%. And if you need the exact reference to the paragraph that's in the document, I can certainly forward that.
Okay.
Yeah.
Great.
It's easy.
Any other questions? Go ahead and you can please send those in right now. If not, we're going to wrap it up here. We'll keep it short today. You've got OGI classes coming up. I just maybe briefly, what do they get out of the 3.5? What's a 3-day class?
It's
right?
It's a 2.5 day class. Yeah. We put them through the ringer. These are expensive cameras, can be very expensive cameras, and a lot of people come in totally intimidated. Yeah, I have a camera that's worth more than my salary a lot of times.
Yeah.
And what do I do with it? And so we talk about the conditions necessary for successful gas imaging. Matter of fact, I have a whole presentation, one whole section of that is how do we make really good videos. And so it's all about the camera operation, a little bit about the theory behind it, because if you don't know what gas you're looking for, you don't know which camera to select, either purchase or rent. And so we just focus in on that on a general basis. So it's a 2.5 day. Always bring a lab with us. We go outside if possible and flow a little bit of propane, give everybody a chance to check it out with their own cameras.
Great.
Yeah.
Great. Let's see. I had a question came in. What is the best temperature setting on the scanner, I guess, with HSM when the equipment you're scanning looks like exceeds maybe 90 degrees Celsius?
Oh, you can go to, you'd have to be in the temperature range of the camera. Now these cameras, because they are a cool detector, they go without any sort of attenuation. They go up, I believe, to, 350 C, I believe, somewhere around there. And so anything below that, you have to be in the right range. I think they're like either 7 or 9 ranges in the camera. I think it's 9.
No.
I'd have to go back and take a look. But each one, the reason why there are so many ranges, as opposed to a long wave camera that goes from 0 to 2000 C in 3 ranges, is that the detector saturates very rapidly. It's a very, very, very efficient at counting photons, quantum efficiency. And so what we have to do is we have to narrow down the temperature span. And so you just change a range. So if you're looking at something at 90 C, you're not going to be able to see it if the top of your range is at 50 C. If you need to go higher than 350 C, you can just put some sort of attenuating medium there. I've looked through little 1/4-inch holes. So I take a lens cap, drill a 1/4-inch hole, turn it backwards there, and it attenuates the signal. It basically stops down the lens.
Okay.
And so there are a number of ways to get higher temperature. You couldn't measure temperature through there, but you can certainly image a gas.
Okay.
Yeah.
Great.
Yeah, excellent.
Great. Well, I think we'll wrap it up on that, Ron.
Excellent. Very good.
Appreciate it. Thank you very much.
Yep.
And thank you, everyone, for joining us here for today's webinar on the basics of OGI. As I mentioned, a rough cut will be pushed out via email here probably by tomorrow, and then we'll have a final version of this presentation available in the coming weeks on our website at infraredtraining.com/webinars. Well, until next time, Ron.
Until next time.
Thanks for watching, folks. We'll see you online again soon.